Hello, chemistry students. Good afternoon. I hope everybody has had a great day so far. Man, I'm so excited today. We get to start a brand new chapter number 11. Man, moving right along through the textbook. You guys are doing a great job. Hope the test was okay yesterday. I know it probably was a little bit challenging at points, but I hope you did okay on it. I'm sure you did, and I'll get those graded and back to you as soon as I get back in town. But I hope you're having a great day today, man. We're starting a new chapter in chemistry. Can't be much better than this. The entire chapter of chapter 11 is talking about solids and liquids. Now, we've already talked about gases. That was last chapter. So now we're completely talking about solids and liquids. So actually some pretty interesting things. In my opinion, a little bit more interesting than gases in some ways because we can see solids and liquids and we understand the importance that they have in our world today. So we're going to start talking about it. So open your ebooks to page 284 and we're going to start talking about a couple of intermolecular forces. Now, we've talked about this a little bit already this year. We mentioned the electrostatic attractions between atoms and the molecules and how they bond together and all that stuff. But we're going to get even more specific today and talk a little bit about it and how it all works. And it's actually quite fascinating. So hopefully by now you're on page 284 in your ebooks, and you'll see at the top 11A, intermolecular forces. So some of the objectives of this particular section are to compare dipole-dipole forces, hydrogen bonds, and dispersion forces to predict the possible intermolecular forces present, and then relate physical properties to these particular forces. So that's what we're going to be talking about. And I know probably none of that made any sense whatsoever, but it will by the end of this particular lesson. So intermolecular forces, what are we talking about here? Well, intermolecular forces are electrostatic attraction between molecules. So before we were just talking about how electrons, protons, neutrons, how all that stays together, the electrostatic attractions. But now we're kind of branching out from that and talking about how one molecule may bond with another molecule. Going back to last chapter, for instance, we talked about molar volume. 22.4 liters of any gas is equal to 1 mole of that gas, which is equal to 6.022 times 10 to the 23rd power atoms or molecules of that particular gas. But the question is, what holds those gas molecules together? Well, we understand with gases, each molecule is moving very random. So the electrostatic attractions between each gas molecule is a non-existent, well, maybe exists a little bit, but other than slight interactions between the elasticity of their reactions, they're not going to interact that much. But when we're talking about the states of a liquid and solid, it's completely different. As we've already talked about with the kinetic molecular theory, the molecules of a liquid are kind of moving, vibrating back and forth, almost in a fluid motion, like a wave. But then you have the solid molecules, and those are very rigid, but they're vibrating quickly back and forth. So the question is, what holds them together? What holds a liquid together and what holds a solid together? Why aren't those molecules flying around everywhere like a gas, like gas molecules are? Well, it's all based on intermolecular forces. Intermolecular forces, once again, are the electrostatic attraction between actual molecules, not electrons, protons, neutrons, but actual molecules. Although weaker than the strength of molecules with bonds within molecules, these forces influence the physical properties of many substances. So again, the electrostatic attraction, we talked about the principal energy levels with Bohr's model and all that stuff. That is very important when it comes to the actual strength and structure of a molecular bond. But it's not just that. It's just not subatomic forces. It's actually forces holding molecules together. So the intermolecular forces are classified into three groups, each a result of attractions between regions of charge on some molecules and regions of opposite charges on other molecules. So maybe an electron of one molecule could be attracted to the proton of another molecule. That's what we're talking about here. Okay, so there's three of them. The first one we're going to talk about is something called dipole-dipole forces. Dipole-dipole forces are present when it's a polar molecule and when it has regions of unevenly distributed electrical charges. Now, you guys may not want to hear this, but the chapter that we talked about with the molecular structure, the geometry involved in that, allows us to tell if something has dipole-dipole force. If you guys remember that lab we did where we had the chart and the question I asked was, does the molecule contain polar bonds? And you would answer yes or no. And then we would ask the question, is the entire molecule polar? And you would say yes or no based on if the electron negativity canceled out. I'll put an example on the screen here real fast. I'll just remind you of what I was talking about. Like if I had CH4. CH4 in its molecular form would look like this. You guys probably remember this. And you're probably moaning right now that I have this up on the screen. Well, we would ask the question, does it contain polar bonds? And the answer was always yes, because there's a difference in the electron negativity between hydrogen and carbon. But if you guys remember, we would also ask the question, is the entire molecule polar? And this molecule here, all those polarities or electron negativities would cancel out. So we would say, no, this is not a polar molecule. Well, since it's not a polar molecule, it does not exhibit dipole-dipole force. However, we had this as an example, ammonia, NH3. And this one would, nitrogen would be in the middle, hydrogens would be on the sides and on the bottom, and then we would have two unbonded electrons there. So when we canceled everything out, this would cancel, but the hydrogen down here at the bottom did not have anything to cancel. So we would answer this question, does the molecule contain polar bonds? Yes, it does. But is the entire molecule polar? And the answer is yes, it is polar. So since the molecule is polar, what actually attracts this to another ammonia molecule, maybe it's over here floating around, this one's going to be attracted to this one, and that attraction is going to be called dipole-dipole forces. So whenever there's a polar molecule, it always is going to exhibit a dipole-dipole force. Polar molecules have regions of unevenly distributed electrons. These extra two up here is what I'm talking about. And polar molecules align themselves so that the opposite regions are going to attract. Those two molecules will attract to each other. So that's how we understand that there's dipole-dipole force whenever the molecule is polar. The next force we're going to talk about is a hydrogen bond. Now this one's probably a little bit easier because hydrogen bonds are only present when hydrogen bonds directly to fluorine, oxygen, or nitrogen. So if you have a molecule and hydrogen bonds directly to that, then it's going to exhibit a hydrogen bond. Example of this would be simple, hydrofluoric acid or hydrogen fluoride. That hydrogen is bonded directly to fluorine, so that bond right there is an example of a hydrogen bond. Now I need to say something here, I don't want to confuse you. Bonds, intermolecular forces, they can have multiple molecules that bond together can have multiple intermolecular forces. Because this is an example of a hydrogen bond, but then we would ask the question, is it a polar molecule? And actually this one is. If I ask you guys to draw the dipole moment, it would look like that, if you guys can recall that. Since this is a polar molecule, it would also exhibit dipole-dipole force. So this is an example of one that exhibits hydrogen bonds and also dipole-dipole force. So you got to make sure you're able to distinguish that. But hydrogen bond, the key thing, and I'll put it back up here on the screen, the key thing is hydrogen bonds have to be bonded directly to fluorine, oxygen, and nitrogen. The hydrogen nucleus is left exposed. It's the strongest of all intermolecular forces. That's important also to get down in your notes. So make sure you take the time to do that. Again, I'll leave the slide up here for just a second so you can make sure you get those last points down. Hydrogen nucleus is left exposed, and it's the strongest of all intermolecular forces. All right, so moving right along here. Hydrogen bonds in water have a great effect on the physical property of water. So much so that water can actually bend. If I was there in class today, I would show you this. I'll show you this when I get back. I'll take a balloon, rub it on my head against my hair to cause some static electricity, and then I'll take you guys to a running area of water. And what happens is the water actually bends into the force because it's such a polar bond, hydrogen bond, and the polarity is so strong that it actually is going to be attracted to the water. Pretty cool how that works. The water, I should say, is going to be attracted to the electrical charge in the balloon. It's pretty cool how it works. But hydrogen bond and water have a great effect on the physical properties of water. And we'll talk about that when we get to the chapter on water. For instance, why does ice as a solid not sink in the liquid state of water, which H2O, which is water? Why does ice not sink in water? There's an actual reason for that. It's based on the hydrogen bond. So it's actually pretty neat. In fact, you see on page 285, that table, 11-1 hydrogen compounds compared. You have hydrogen telluride, hydrogen psyllium, hydrogen sulfide, and water. Look at the molar masses. They're all similar. You can see water gets less and less and less. H2O has the smallest one. But look at the melting points. This is amazing. Water melts, we know, at 0 degrees. Now, it also freezes, but don't forget, the freezing point and melting point of a substance is the same. So water melts at 0 degrees Celsius, but it also freezes at 0 degrees Celsius. We'll compare that to the first one, hydrogen tellurium or telluride. It boils or melts, at negative 49 degrees Celsius. Y'all think about that. A substance literally starts to melt at negative 49 degrees Celsius. That's mind-boggling. But what's even crazier is look at hydrogen telluride's boiling point. It actually boils at negative 2 degrees Celsius. That's fascinating. And then you see the hydrogen selenium or selenide, and then you see hydrogen sulfide. Those boiling points are very, very low. 2 degrees, negative 2 degrees Celsius, negative 41 degrees Celsius, negative 59.6 degrees Celsius. That's impossible for us to imagine something actually boiling at negative 59.6 degrees Celsius, yet it does. But what's fascinating is look at water. Water is such great difference between those. It's 0 degrees Celsius for a melting point, but its boiling point is 100 degrees Celsius. This is extremely important, and it actually allows us to basically live off of water. Think about water boiling at a negative degree Celsius. None of us would be able to have water. It's really mind-boggling, but we'll talk about it, like I said, at a different chapter. It's pretty cool to think about and consider. Water molecules are quite polar. All right, there's one more force, and this is the last force that you're going to have to know. The last force is dispersion force, also called London force, named after the scientist who actually came up with this. So London force or dispersion force results from random unequally dispersion of electrons around an atom in a molecule. It's temporary dipole. It goes back and forth. And the key here about dispersion force, it's the only intermolecular forces acted on nonpolar molecules. So if you have a molecule, remember, a molecule is defined in this textbook as a covalent bond. So I'll just put one up on the screen here, something simple. Let me think of one. Yeah, CH4. If we drew that out, you don't even have to draw it out. Let's talk about what forces. This is what the test question will ask, what the homework will ask. What forces, intermolecular forces, are present in this particular molecule? Well, first, it's a molecule because it's a carbon, a nonmetal bonded to hydrogen, another nonmetal. So we know it's a molecule. Since it's a molecule, we know it's going to have dispersion force. All molecules have dispersion force. So then you got to ask the next question. There's two other forces, hydrogen bonds and dipole-dipole force. Well, to figure out the dipole-dipole, you draw out the molecular shape. All of the electron negativities cancel out on this one. So we know this is not a dipole-dipole. There's no force here for that. I also know there's no hydrogen bond present as well. You got to remember, hydrogen bonds are only bonds between hydrogen bonded directly to nitrogen, oxygen, and fluorine. Here you have hydrogen, but it's bonded to carbon. So it is not one of those three elements. So the only force present here is dispersion force. Okay, so that's where we finish. That's pretty much the lesson today. Again, it's not super difficult. It's just a matter of trying to think it through and try to figure it out. The homework I want you guys to do is I want you to do the chapter review number 1 and number 2. There's a couple of extra problems in it, like A, B, and C type thing. So flip over there real fast. It's on page 305. I just want to give you an example to make sure you know what's going on here, okay? So on page 305, number 1 says, predict the type of intermolecular forces that act on the molecules. Of course, you could have more than one answer, and we got to figure this out. Now remember, there's only 3 forces that we have to worry about. There's dipole-dipole, and then you have hydrogen, and then we have the last one, which is dispersion. Also called, dispersion is also called London, but when you answer it, it's easier just to put dispersion. So remember, with dipole-dipole, you have to have polarity. The molecule has to be polar. With hydrogen, hydrogen has to be bonded directly to nitrogen, oxygen, or fluorine. And then dispersion is present in all molecules. So I'll give you a clue. A, B, and C, A, B, C, and D on this exercise are all molecules. So you know every single one of them has dispersion force. Okay, so let's check it out. The first one, I'm going to do the first one for you. Letter A here is CO2. CO2, we know this is carbon dioxide, so we have to determine what forces are present in this particular molecule. Well, in order to do it properly, you really need to go back and you need to draw the electron dot structure of this. So we know carbon's going to be in the middle. It has 4 valence electrons. We have oxygen. I'm just going to put it on the sides for now. Oxygen has 6. One has to go there. So that's 1, 2, 3, 4, 5, and 6. One of them have to go here. 2, 3, 4, 5, and 6. Well, hopefully you guys remember this. It's not complete because I don't have 8 in each outer valence electrons. So we have to, it doesn't follow the octet rule. So we need to make it do that. So hopefully y'all remember, I'm just going to take this electron and move it here, move this one down. I'll take this one, move it around, and take this one and move it here. And when you do that, you get carbon, and it's going to have a double covalent bond to this oxygen, a double covalent bond to this oxygen, and then these are the extra electrons that were left over from the oxygen. So this will be the electron dot structure, or the Lewis dot structure for this. Now notice, the reason you have to do this is because you have to check if it's polar. Obviously, we know hydrogen is not present. The reason I know hydrogen is not present is because CO2 doesn't have hydrogen in it, so it's not going to have hydrogen bonds. It has dispersion. I know it has dispersion. That's a check on that one because it's a molecule. It is not hydrogen because it doesn't have a hydrogen molecule or atom. So I got to check for polarity. And you guys hopefully remember here, based on my drawing of the Lewis dot structure, this electron negativity and this electron negativity cancel out. And there's no electron in here or here in those 2 orbitals. So I know that this has no polarity. So there's no dipole-dipole moment. So there is no dipole-dipole force. So that's what you're going to do on the first exercise here. The second exercise is based on your knowledge of what's going to happen. If you flip back in your textbook, there's a very important chart on page 287. 287, 11-2, you need to get this down in your notes and you need to have this memorized. If you have an ionic bond, which we're not going to worry about on this one, look at its properties. It has a very high melting point or boiling point, usually soluble in polar solvents. So ionic is very high in its melting and boiling point. If you have a metallic bond, then it's also going to be very high in its boiling point. The one I want you guys to focus on is the polar molecules and the nonpolar molecules, because that's what we're talking about in this chapter, this particular section specifically. We're talking about molecules. So if you go through and you do what we just did on the screen, and you notice on the one on the screen that the only force present is dispersion. Now notice on that chart with dispersion forces, if that's the only thing that's present, it usually has a very low melting point and a very low boiling point. But look on the one right above that where it says polar molecules, dispersion force, dipole-dipole force, possible hydrogen bonds, that's when the melting point is going to be slightly higher. So polar molecules have a slightly higher boiling point than nonpolar molecules. If you want to look at it in a chart, if you have an ionic bond, remember, is a bond between a metal and a nonmetal. An ionic bond is what I should put up here. That's going to have the greatest. That's going to have a greater melting point, boiling point than a cation or a metalloid. Remember, a metalloid is, or a metallic bond is what I'm going to put, not a metalloid, a metallic bond. And then that's going to be greater than a polar bond, and that's going to be greater than a nonpolar bond. So that's the sequence. Ionic has the highest, and then maybe I'll put high here for its high, and then polar is low, and then nonpolar is lowest. So if it asks the question, compare one to another, like it does on number 2 on the chapter review that you guys are going to be working on, what it's talking about there, you're just comparing the particular molecules to see what actually is going on here. So again, I'm trying to flip to it real quick on my textbook. Back to the chapter review here, sorry. I kind of got lost. Here we go. Yeah, so number 2, you're comparing some different pieces. I'll do a very simple one. If you look at 2B, you're comparing the compound NaCl and you're comparing that with the molecule HCl. And the question is, determine which substance of the pair should have the higher boiling point. Well, this one's pretty easy because NaCl, you guys hopefully remember NaCl is salt. That's sodium and chlorine. Sodium is a metal, chlorine is a nonmetal, so this is an ionic bond. And then you look at HCl. HCl, when you draw it all out, H bonded to Cl, it is going to have dipole-dipole force here because there's a difference in electron negativity. So it's going to be polar. So this is polar. So the question is, which one of these has the higher boiling point? Well, the little chart that I have, or little sequence I have here up here, I have on the screen, I should say, should help you understand. Ionic has the highest. So salt is going to have the higher boiling point between salt and hydrochloric acid. So that's what it's asking you to do. Not super hard. You just have to understand this little chart right here that I have on the screen. That'll help summarize that chart that I told you guys to look at. Well, that's pretty much it, guys. That's section A. I hope it's been pretty straightforward for you. It's not super difficult. It's just kind of, you got to memorize a couple things. But if you'll take the time to do that, I don't think you guys are going to have any trouble on this particular exercise and this homework. Make sure, again, you're working on your science projects. I'll be checking up on you guys on Monday because since I'm not here on tomorrow, but I'll check with you guys on Monday, make sure things are going well. Have a fantastic day. I hope you guys do well for the remainder of the day. And, of course, although I'm not there, I'm thinking of you. And I hope this lesson and I hope your homework goes well tonight.